welcome to this lecture. Now we will see a very important property of an antenna, of a receiving antenna, by which again we can find out lot of things, particularly how much power an antenna is receiving. That will be helped if we can find this parameter. This is called effective aperture of an antenna. Actually, every antenna has an effective aperture, but you see that when we talk of wire antenna, we say that ideally that has only a length. So, it does not have any width. So, its area is 0, but please remember that its physical area may be 0 or very small because its width is small, but to be an antenna it should have a high effective area. That effective area is actually an electrical concept, it is not a physical area thing. So, effective area, if it is not high, then it is not an antenna and it will not be able to take the power take from there. Actually, any antenna's job is, suppose there are lot of here waves going on. So, to extract power, so that it will not be able to do if it does not have a sizable effective area. Now, for other aperture antennas, it is not difficult to visualize this effective aperture, because you see that larger and larger, if I make a aperture, then aperture will take more power, and obviously all the powers I cannot take, because then I require uniform illumination over the whole aperture. So, because of the non-uniformness in the illumination, the effective aperture of a aperture antenna is always less than the physical one. So, we will have to find out from the knowledge of field theory that how much is the effective aperture, how much it is less than 1. But so, now we can unify that whether it is an wire type antenna or aperture type antenna or a mixture of that, anything. So, that has an always has an aperture. So, and that what is the concept of that aperture? We consider that it is the area which, because any place we know in the field theory, ultimately if I know the antenna is either radiating or receiving. So, at this point what is the radiation, what we call the power density, that we can always find out, because we know the what is the electric and magnetic field, from that we can always find the power density at a point. Now, point is whatever total power the antenna is taking, that is nothing but that power density multiplied by the effective area. So, I can say that suppose I have this is an antenna and some electromagnetic wave, incident wave is coming. So, at this point I have some power density. Now, this power density, it is unit is watts per meter square. Now, that multiplied by effective area of the antenna, that should give me the total power received by the antenna, received or extracted by the antenna. So, I can say that if power density, we generally have this expression Wi symbol, effective area is AE. So, this is I can say total power. So, this is the formula for effective area. So, effective area, it is generally it will be unit is meter square, this is watts per meter square and this is watts. So, total power received by the antenna, or you can say how do I measure total power received by the antenna? You can say total power received by the antenna and delivered to the load, or total power received by the load, because ultimately the antenna will be connected to a load. So, whatever total power received, because I cannot measure what is the power received by the antenna, that we can measure across a load. So, better we can correct the thing, the total power received by the load or delivered to the load. Okay. So, now let us see that for an antenna how to find it. So, I can now write that effective area AE is PT, or I can, there will be some confusion with the letter nomenclature. So, let us make it PT. So, AE is equal to PT by Wi is half. So, what is PT? Half IT star, that is IT mod square. This IT we have seen in the case of input impedance, that in the receiving mode, this is the, in the Thevenin equivalent circuit, this is the current that is flowing, and RT is that there. I think I have that slide here. This is the Thevenin circuit. So, RTXT. So, how much will be the power in the load, that we can calculate from here, half IT square, IT mod square into RT. That is what I am writing. So, this we have already seen. So, then what is now I have all these expressions there. So, can I write directly that half IT square. So, AE will be VT square by 2 y RT by RA again under conjugate matching, when we say that we are getting maximum power to the load under conjugate matching. So, this AE effective area, obviously maximum power will be delivered there. So, we can that time call the AE as AE max. So, effective aperture become maximum. So, you see that it is a electrical concept, that under conjugate matching the AE value is changing. Under conjugate matching its value is changed to maximum. So, AE of a antenna is not a fixed thing, but it changes if you have matching with the external or generator impedances etc., load impedance etc. And so, its value will be, if you put it, conjugate matching means what is the condition of conjugate matching? Let me write that RA plus RL will be equal to RT and XA will be equal to minus XT. So, then this thing will be VT square by 8 Wi, then say RA plus RL. So, actually if there is no polarization mismatch, then just later will show by a thought experiment that this actually A max value, this will be equal to lambda naught square by 4 pi into g. This will prove, but you write here that this is the maximum value. So, you see that if you know the operating frequency, you know lambda naught, and then actually this effective maximum effective area of any antenna is related to another measurable quantity of the antenna, that is G. What is G? G is the maximum value of G theta, that means the gain of the antenna. Now, gain of the antenna we always define as a transmitting thing. So, you see that this is a connection between the receiving characteristic and the transmitting characteristic of the antenna. So, transmitting characteristic is G, we know how to measure G, you find the power pattern, you find what is the power distribution at various points, and from that you can find out what is the maximum G. So, you can now find if we the same antenna we use as a receiving antenna, what is the relation, what will be its effective area. So, that the same antenna which you have characterized with its spatial gain, now you know that if I use it as a receiving antenna, how much power it will be able to find out. So, I have already said that this effective area, it is some portion of the physical area, or that means the for a aperture antenna, the effective area AE, we can say some fraction of the physical area of the antenna, always it is less than the physical area. And this thing we have also seen that actually the electrical distance of the antenna determines its area. In case of wire antenna, it is, as I already said, that it is very much greater than its physical area. So, the case is opposite. In case of aperture antenna, the effective area is less than the physical area. In case of wire antenna, the physical area, the effective area is much greater than the physical area, otherwise it cannot be used as a thing. Now, let us go to prove that point. This is a very important relation, various times we will use this in most of the models of communication, radar, etc. This formula is used, but to prove this we need to find out one thing. This effective area concept we have introduced. Actually, when we have introduced in the start of the lectures the current element, we have found some of the parameters, antenna parameters of current element, but we have not found its effective area. So, let us find that, because effective area of a current element is a very useful quantity, because that time we have seen that it is not a very good radiator. That means, we said that its radiation efficiency is not very high, that we calculated that time. But otherwise, as a directive characteristic of current element is very good, that we have not found, because we have neither found the gain nor found the effective area of the current element. The reason is basically that time we have not introduced this concept. So, let us do it now. So, suppose I have a current element and there is a incident wave coming, and we assume that this incident wave, this current element is z directed and incident wave is also z directed. So, there is no polarization mismatch between the current element and the incident wave. Also we assume it is a lossless current element, that means its RL is 0. So, what will be its AE max from our relation, because we have last found this relation that Ae max is V t square by 8 Wi R a plus R L. So, here if I put, so it will be V t square by 8 Wi R a, because I am taking R L is equal to 0. Now, what is V t for a current element? You see, I have an E electric field and I know that this distance is thing. So, can I say that V t is E into d l, and what is W I? Now, here we are assuming that this incident wave is coming from a source which is at the far field. So, actually it is a plane wave is coming. So, what is W I for plane wave? We know for plane wave this power density at this point on the antenna where I am capturing. What is the power density? Can I write it is E square by 2 Z naught, where Z naught is the, or earlier you used to call it, sorry, it is eta naught is better to say, E square by 2 eta naught, where eta naught is the intrinsic impedance of free space, that is 377 ohm. Okay. So, let us put it now. So, it is E d l square by 8 E square by 2 eta naught, and this value we found for current element. What is R A? If you see your notes, it is 80 pi square d l square by lambda naught square. So, if you simplify, this will come to 3 lambda square by 8 pi is equal to 0.119 lambda naught square. So, the above value is only valid, that means we have got this. So, let me write again Ae max of a current element this is 0.119 lambda naught square. So, this is for a lossless current element, and obviously, the losses for a this type of current element is quite small, but if it loss is sizable, that means if actually for current element the radiation resistance, this 80 pi square d l square by lambda naught square is also very high. So, if we take that, that means there are losses, and let us say that R A is equal to R L. In that case, the total R T that will be 2 R A, and so that time the Ae max value will become half of this. So, for a lossy antenna, lossy current element, the Ae max will be less also. Now, let us have some typical values. Actually, suppose we will see later that the dipole, it can be considered a current element, a dipole can be considered as a current element if its length by the frequency of operation is less than 1 by 50. So, if I have a dipole of length lambda naught by 50, then its Ae max, I am assuming lossless. So, Ae max is 0.119 lambda naught square. Now, what is Ae max? L into width, effective width is W e. that is 0.119 lambda naught square. Now, length I have assumed lambda naught by 50 into WE is 0.119 lambda naught square. So, if you do that, what is the value of effective width? 5.95 lambda naught square. So, physical generally dipoles, when we design we will see that dipoles, the physical dimension or physical width of a dipole is generally the physical diameters of dipole are lambda by 300. So, it becomes the WE, this is actually 1785 D. So, this is the thing, actually effective width or electrical width of a dipole or a current element, if that is almost 1500 times its physical day, and that gives us is the effective area. As I said that for current watt type of antennas, the effective area is much small, much larger than its physical area. Basically, the width gets jacked up, otherwise it cannot be used. Now, let us do another trick, that if you believe, actually we will just prove this formula, but if you believe this. So, I have already found out the Ae max for current element. So, what is the value of the gain of a current element? That also we have not found. Generally, we find it, and I think in assignment it will be given that find the gain of a current element. Find the gain of a current element. So, G, find out G from here. So, what will be the value of G? Ae max is for current element 0.119 lambda naught square into 4 pi by lambda naught square. So, lambda naught square will cancel, 4 pi roughly 12 into 0.12, 0.12 into 12. So, it is 1.44. The actual value is, if you do, it will be 1.5. So, roughly the gain of a thing is 1.5. That means, compared to an isotropic antenna, the maximum direction when current element, we have seen where is the maximum direction of a current element's radiation. The radiation pattern of current element is something that in this direction it is having maximum radiation. So, compared to an isotropic antenna, it pumps 1.5 times power in this direction, and that is not bad. A practical antenna like dipole, a resonant dipole, half wave dipole, that has a gain of 1.67. So, we can say that current element, earlier we have discussed when we introduced the thing, that current element is a hopeless radiator, because its radiation resistance is very low, but it has a very good characteristic, it has a very good directive characteristic. So, that is why current element we studied for many other things. That time we said that it is same gives us very good picture about what happens for other complicated antennas. For all complicated antennas, some general things we derive from current element, but it also is a very good radiator because of its structure, because of its geometry, and that is proved here. So, this value actually again I will use in the next one. So, now I will find out, I will do a thought experiment to prove to you this formula. That means, we will have to prove this formula, because this I have not proved. Ae max, that means what is the relation between transmitting gain and effective aperture. So, that I will prove now. So, for that consider two antennas separated by a distance r. So, this is an antenna, this is an antenna separated by a distance r. They are in the far field of each other, and let us say that this is a transmitting antenna, this is a receiving antenna. So, whatever this is transmitting, this is receiving. How much it is transmitting? Let us say that it is transmitting Pt amount of power, then its directivity is dgt in this direction, or I can say maximum directivity in this direction, or directivity in this direction receiving, that is dgt. You see T subscript I am using because it is a transmitter, and its area, effective area is AE, or I can write ATM, a maximum effective area for this case, and the corresponding things for these antennas are ARM and DGR. Okay. So, that means basically this PT is later comes. So, actually antennas are, these are the characteristic ATM and DGT for these, ARM, DGR for these, because these are receiving antenna, these are transmitting antenna. Now, what is the power density at this point if this antenna is connected to a transmitter of power PT? Can I say that WT here, that will be that PT by 4 pi r square, because this is a far field spherical wave, into DGT. We are assuming not gain, we are saying directivity. Okay. That means lossless antenna and efficiency 1. Okay. Now, so the how much power this antenna will collect? Power collected will be PR is equal to WT into AR. So, that will be, I am not writing M because M is the maximum of that, I am writing in general AR. So, that is PT DGT AR by 4 pi r square. From here, can I write DGT AR is equal to PR by PT 4 pi r square. Okay. Now, I invoke a theorem called reciprocity theorem. So, I say that if antenna 2 is now used as a transmitter, antenna this one as a receiver, and the intervening medium is linear, passive and isotropic. That means, whatever is called simple medium, then can I write that you do this thing, that now this is transmitting PT, this is receiving PR, the things are same. So, if we again write, we can prove that DGR AT will be equal to PR by PT 4 pi r square. So, from this we say that DGT AR is equal to DGR AT. So, I will write that DGT AR is equal to DGR AT, or DGT by AT is equal to DGR by AR. This relation says that increasing directivity of an antenna increases its effective aperture in the same proportion. So, if ATM and ARM are maximum effective aperture of antenna 1 and 2 respectively, then we can write DT by ATM is equal to DR by ARM, where DT and DR are the maximum values of the directivities. Now, You see this relation is valid for all the antennas. Consider that the first one is an isotropic antenna. If it is an isotropic antenna, its maximum directivity is 1. So, we can write ATM is equal to ARM by DR. So, what is the maximum effective area of an isotropic antenna? It is equal to the ratio of the maximum effective area to maximum directivity of any other antenna. I repeat, the maximum effective area of an isotropic antenna is equal to the ratio of the maximum effective area to maximum directivity of any other antenna. Let me choose that any other antenna to be current element, because I know these two value for the current element. So, put it. So, what is the maximum effective area of the current element? It is 0.119 lambda naught square, and what is dr? That is 1.5. So, find out this is nothing but so this value is how much? Lambda naught square by 4 pi. So, we can say that lambda naught square by 4 pi is equal to ARM by DR. So, from here we can say that AE max of any antenna, because now R and R subscript I am leaving. So, this is true for any general antenna. So, AE max is nothing but lambda naught square by 4 pi into D max or something. Now, many times you will see that time we have written it as gain. So, it is a gain. So, this formula is proved that A max is lambda naught square by 4 pi. Instead of D max, we are calling it gain. If there are those efficiencies involved, that should be factored into here. So, this is a very useful thing, but if obviously if this here we have assumed that the antennas are lossless, the antennas there are no polarization mismatch, there are no impedance mismatch, etc. If that is there, all that should be factored here as the efficiencies, but this is a very useful relation, because if I know transmission characteristic of any antenna, this helps me to find the receiving characteristic of the antenna. So, this route is through the effective area of the antenna, that is why it is a very important parameter for the antenna. Thank you.